Right. Good afternoon, everyone, and welcome back to the AI for Earth System Science Summer School. For our afternoon schedule, we're going to first do our panel from 120 to 150. Then after that, we're going to provide everyone an overview of all of the solutions that were submitted for the hackathon. Starting at about 150, I'll do an overview, kind of a quick overview of the hackathon and what went on, what we learned. Then our schedule is 2 o'clock will be El Nino. We'll cover that. Then around 2:50 we'll do holodeck. We'll take a break at 3:30 for 10 minutes, and then we'll wrap up with microphysics, gecko, and GOES between 3:40 and 5. For those of you who can make it, we'll also record all these presentations and post the slides online so that you can see what happened. We're also planning for the Jupiter Hub will keep running at a little bit more limited capacity for the next few days or so. Still have a fair bit of Amazon money left, so we can keep it going. But beyond that, you feel free to log in, use the Google Colab links to work on the problems. Even if you haven't done the hackathon at all, we encourage you to try them out, and we'll keep refining them based off of feedback from this week. We'll also be sending out a survey to people who registered for the hackathon and for the lectures to get more information about what went well, what could be improved, and just if you have any general thoughts. And also please feel free to email myself or Tasia with any other feedback you have about the hackathon and the summer school in general. So with that, we'll turn over to the speakers and from this morning, and we'll go through a few more questions. If you want to go ahead and post the Slido link. So our first question is, how are spatial correlations handled when downscaling to a distribution rather than a single output? I.e., the value in the location changes distribution in location A changes the distribution in location B.
I guess that's to me.
Yeah, I think so. Yeah.
So oh, okay. There might be a way. So I'm answering Sebastian's question. There might be a way to map to distributions over locations, but actually the way we were doing it was our model would have a distribution over such maps. So if you give me an input map at the coarse grain resolution, I can sample, I can do conditional samples conditioned on that image and give you a whole distribution over over entire images at the fine-grained resolution. So it doesn't really directly address your question, but that's what our architecture does.
Thank you. Thank you, Claire. Next question. I think this could be either, again, for Claire or for Mustafa. Can you give any concrete examples of how a GAN would be useful in climate modeling?
So there was a cool contributed talk at CI 2019 on GANs for cloud types. I've seen GANs for precipitation, but keep in mind, Mustafa raised a lot of the concerns about GANs, and basically either you're making some distributional assumption on the noise process. Basically, the issue with GANs is that it's an open question in AI to even evaluate the distribution that they generate. So when I saw the CI talk on GANs for precipitation maps, I believe some open questions were, how do we tell if the distribution represents the accurate distribution over precipitation maps? And I kind of smirked because this is actually a larger open question in machine learning. But I guess we talked about how other generative models could potentially be useful. And so for climate modeling in particular, I don't know if somebody else wants to maybe comment on that.
Mustafa, Pierre, Karthik.
Yeah, I could add a couple of comments. Along with Mustafa and others at NERSC, we've trained some GANs to mimic relatively simple, but based on sort of climate dynamics. So atmospheric convection using a Rayleigh-Bénard convection system. There's a recent paper in JCP on constraining some of these GANs to capture the right spatial statistics of Rayleigh-Bénard convection. Mustafa is actively working on style GAN, which I think we're writing up fairly soon to reproduce some other high resolution variables of 25-kilometer climate model. So there's definitely work in progress. I think there's still a long way to go before we solve the problem. And we're still learning how to exactly evaluate these GANs and what types of characteristics do we care about and so on. Do you have anything to add, Mustafa?
Yeah, so again, just a caveat, I'm not a climate expert. But the way that I see it is that, so at a very high level, the problem of modeling a system like a climate system, for example, is a spatiotemporal modeling problem, right? And then the hope that we're looking for here is that can we use any of these methods, GAN or other methods, to do some to incorporate some real data into the systems, or to do like a data-driven sort of modeling. You can think of it as a surrogate modeling. So you have either surrogate modeling as you train the model on simulations, and then you have a much faster, less computationally expensive surrogate model for your simulator. Or you can think of it as like, can I get rid of the whole simulator and then train on real data, or use real data to predict, for example, future trends? Or can I incorporate both simulations and then have some sort of like injecting or constraining the system by real data? In all of these problems, it's the general space of like spatial, what sort of things we can do in the space of neural networks and spatial temporal modeling. And in this case, you can think of GANs, you can think of one way to do all of solve the spatial temporal problem is that to say, like, I'm gonna decompose the problem into spatial modeling and then temporal modeling. And if you're doing this, again, I'm just giving a particular setup. It's not necessarily the only thing that you can do. You can think of it as like, I'm gonna split decompose the temporal modeling from the spatial modeling problem, then go and learn the spatial distribution of all possible, essentially find the real data manifold for the spatial distributions, and then do temporal modeling in the latent space. That's one thing that you can try, right? Like, so once you have a GAN, let's say a GAN that produces every single point in the prior space, goes to a spatially meaningful and physically coherent spatial data point, then I can go and then try to do, for example, temporal modeling in the latent space. And that's something that we are working on. But the general picture is these models seem to be really, really good at capturing higher order correlations in spatial distributions, and also they are good at like doing a density estimation for data like that look like images and have some spatial distribution. And then we're thinking of how can we actually use that in the space of climate modeling. Yeah, I mean that's one way, one possible use. I think the experts would probably have better ideas.
Maybe if I could add something. So, I mean, kind of the way I see, sorry, my daughter is here. So one of the ways I kind of see the use of GAN, and I think they are very powerful, is one way is to basically generate things for cheap, right? I mean, a lot of the complexity we have is those models are really expensive. So that's one thing that's very useful. The other one is for like process level understanding. And I think Mustafa, you gave some great examples, like, you know, that for instance, any bottleneck like in variational autoencoder or whatever is actually a great way to understand things, right? So that could be actually like focusing on the latent space is very insightful in many ways. But I still feel that for climate, I mean, if it's climate modeling, it depends on what time scale we're actually looking at. But for climate change, if the processes are eventually changing, I mean, whatever model you have, I mean, you would never be able, or machine learning model you have, I mean, you would never be able to get that. And one example we had that was very clear is that if the height of the tropopause is going much, much higher, you can do all the best job in the world. I mean, if you've never seen that before, you've just never seen that before. So, and if, for instance, all of the ecosystems were to die above, like, let's say, 40+ degrees Celsius, I mean, there's just no way you would infer that. And I think we need to be mindful that, you know, in the background, there's lots of things we cannot predict. But there are lots of things we can still cover. And those, I mean, generative models are extremely powerful for many of those intermediate applications. They might be even maybe some of the most exciting tools.
Yeah, so sort of a related point in this area. Can you talk a bit about the interpretability of the latent space of variational autoencoders versus something like normalizing flows or even GANs for that matter? Is there any expectations of getting a latent space that is more interpretable?
So I think this is a good area of research. I think it's mostly pretty open. One thing not in the VAE setting that I'm reminded of is Emmett Ebert-Uphoff and Libby Barnes and like their postdoc had an abstract at AGU where they did a really simple, almost stupid pretext task. It was supervised learning, and the task was take a map, maybe it was a temperature map, and predict the year. So classify the year. So you just had to output a year. It was supervised learning. It was some sort of deep network. I think they maybe used a multi-level perceptron to make it extremely interpretable. And then they visualized which examples made the learned features have the highest activations to see spatially what differentiates two different temperature maps that have spatial features that help us distinguish as to which year it was. So it's the same sort of thing when we think about interpretability of a latent space. You know, ultimately you're doing some kind of task like a VAE, just reconstructing the input. But then when you want to look at the latent space, there might be ways to find interpretability, you know, looking at which training data points provided large activations, but it's mostly pretty open, and I don't off the bat have a good answer. So for example, in the align flow domain alignment technique, how we would interpret the latent space other than, you know, this allows us to align two different domains such that we can get a tractable approximation of the joint PDF.
Yeah, if I can add to this on the point of the latent space. So if you just take a vanilla VAE and you train it, there is no guarantee that you will find certain directions or like the components of the latent representation to correspond to something that is semantically meaningful, right? So what we do in practice is we essentially just do, some exploration of the latent space. So we take one data point, we know that this data point produces a certain thing, let's say like a person with a certain gender, certain color, certain something, and then we take another data point and then we see the vector that is moving between them, try to essentially interpret, like know in which direction we need to move in the latent space so that we change the feature that we're interested in. So this is just the vanilla version, right? But then directly to your question is of how do we actually construct a latent space that where we have a better control over the representations that we are learning. And this is the whole business of style GAN, right? So the idea is you'll see like big part of the paper, and there's the whole field of disentangled representation learning. How do we make sure that the network is learning representations that are completely disentangled? Disentangled as in I move in a certain direction, and then in that direction I'm only changing one thing, right? Like a certain property, gender, for example. Sorry about this. So and in this is what the area of disentangled representations. It's still questionable whether it's something that we hope to do. It's still questionable that we can really, for any real data, produce completely disentangled representations or not. It's still an open question. But style GAN tries to do essentially that. And there's a whole part of the architecture that does style mixing thing, which encourages the network to learn completely disentangled representations at different parts of the architecture. So yeah, it's you can just explore. Essentially, the answer is you can try to explore the latent space, or you can look at things like style GAN to try to construct a space that is interpretable or encouraged to be to have some disentangled representation.
I think it's clear. I mean, we need to make clear that that's really bleeding edge, because there's a lot of theory supporting that it's not possible to disentangle. And also it depends what, like,
Yeah, absolutely.
Sometimes the
That's
things that the human wants to disentangle are not being learned. And then I think in climate, it becomes even more fuzzy, because we're just like looking for objects and patterns on fluids. We don't have like glasses that are non-deformable and that kind of thing.
Yeah, absolutely.
So it's bleeding edge AI, not something necessarily ready for the application.
Next question that's come up. Aren't CNNs a kind of more sophisticated coarse graining? Could you use these to first move to some lower resolution space and I guess learn a way to do that?
Yeah, I mean, what is the goal here though? I don't know. How do they respond? Because I'm not sure.
Yeah, I think this was a question from earlier. Forget exactly which. It might have been with Pierre's talk. That I think it came up.
Yeah, I would say, I mean, in our case, I would say yes to some extent. I mean, the spatial. So what you want is basically you want to capture the some spatial autocovariance. I mean, that's what actually is crucial to get the structure at the cursor scale. So I would say yes. And that could be space time actually. I mean, for the convolution, I mean, that can be 3D time.
I believe that there's also a paper by Stefan Hoyer and other colleagues at Google that was looking at ways to they think learned a coarse graining approach that still tried to approximate the statistics of the system they were trying to model, and they had some success with that. So if you search around for it, you might be able to find that paper.
Yeah. Actually, there's some really interesting work as to how you can actually use that as a way to define PDEs at different scales. And because it's not straightforward, what is the best way? So you could have, I mean, different type of of strategies. So you can actually define that in a very objective way, starting from the supervised learning at the fine scale resolution, and then cross-graining that and defining the best cross-graining for the PE. And how you basically, it's a matter of how you weight those things. You could learn. Very cool work.
Here's another question that's come up, I think is relevant for everyone. I want to keep going, but I'm wary of cost. What guidance do you have for finding and selecting an affordable and accessible resource, including uploading data? So I guess computational, person time. What kinds of setups is everyone using for their machine learning, and what can we use to help other groups get those resources?
So, I mean, I've gotten grants from Google Cloud and also Microsoft AI for Earth. So it's pretty easy to get access to cloud resources for research and educational purposes.
Amazon has been also pretty good, yeah.
Yeah, I mean, one thing that we did initially is if you have a grant where you can buy a GPU box and you can put it in a place that the noise won't annoy people, then somewhere between 7,000 to 10,000 can buy you a box that has 3 to 4 GPUs and pretty decent performance. So a lot of the prototyping can be done on that, and then you can move to somewhere else for large-scale experiments.
And if you're doing more kind of just exploratory type stuff and not like maybe a full-on giant research project, starting with something like Google Colab or Kaggle kernels, which have free GPU and CPU resources that they're in the cloud, and you can upload data onto there and do some computing on decent sized data set. Nothing that's like gigantic, but if you're just getting started out, that is a place to work on it. And there are a lot of problems where you could probably, maybe not running a full GCM machine learning type thing, but there are a lot of kind of smaller, more traditional problems that you can still run on your laptop even. If you just want to like kind of get some practice with the methods, it's good to start simple. And then work on scaling up and out. Another question I saw pop up, it went down here. Oh, here it is. So there's another a little more provocative one. The inpainting example shown almost seemed like an argument against using them for climate data. There could be a radically different feature in that data gap. Any comments on potential issues with the downscaling approaches or inpainting or some of these other techniques, and how they like what might they be missing in the process?
Yeah, I was trying to get, I mean, I didn't mention inpainting directly. I mentioned super resolution. So not all the things coming out of computer vision are necessarily going to be directly applicable here, where we have much finer scale processes that we don't want to abstract away from. So, I mean, one approach would be the domain alignment technique instead that I mentioned, but it is a concern.
If you have like Tibet at the higher resolution, that would be a bummer, right? Mm-hmm. So topography could be.
Yeah, I mean, like there are always there could be always outliers, right? Like that you can't, of course, you can only extrapolate from the distribution that you have learned, and then the truth could be an outlier to that. Adding physical constraints seems to help. You can, if you're adding physical constraints to the model, at least you know that even if its prediction will be somewhat consistent with the physics. So that improves the generalizability, and you would get better sort of guesses or in painting or whatever you're looking for. And if at some point we have models that where the physical constraints are actually incorporated in the architecture, that will even be better, right? Like instead of being soft, just a regularizer that's added to the loss function or something, but you have your architecture respects the conservation laws or symmetries or whatever you want to incorporate. That will give you at least an even better performance with this. But yes, I mean, like if you can only extrapolate from what you have learned, and then if there is something completely outside of that, you won't be able to guess it. It's hard.
Actually, along those lines, I mean, we've tried regularizing using your prior knowledge, based on physics, and that works really well in many contexts. I mean, taking again the example of topography, let's say you would have very high topography, you kind of know what is the lapse rate, that would be your best guess, and you could kind of use that as a regularization. It seems that this helped tremendously in some ways.
Yeah, this is an area that I'm very interested in, and my argument, what we're trying to explore is that it seems that if you use a model and then you add physical constraints, it helps really well. But if you use a better model, you don't need the physical constraint. The model will discover the physics, and then or will respect it, or whatever you want to call it. But it will be, and this is essentially comes in the context of our biggest problems with these models is that we need models that are easy to optimize. And a lot of the models, like all the ingenuity that came on in deep learning is essentially how do we come up with models that are easier to optimize, like adding batch normalizations or going to a much larger model and adding skip connections and all of that stuff. It seems that those more sophisticated models, you can go to larger number of parameters. Once you go to larger number of parameters and you can actually optimize them, you get better performance than smaller models plus physical constraints. And this is related to a topic in deep learning theory that's called the double descent phenomena. This phenomena that if you are plotting the performance of your model as a function of the number of parameters, you expect that at some point, at a certain size of your network, the performance, the generalization performance starts degrading, right? And that's what happens. But then what people discovered is that if you still increase the parameters much larger than that onset of degradation of performance, you get into another descent curve where you have lower performance. Essentially that much larger models perform better than smaller models. And my guess right now is that most of the work that we are doing in science is still stuck at the range where we're using these small models because we're motivated by this idea from traditional machine learning that start small and then start increasing until you get to a certain number of parameters, and then that's it. This is the largest model that you can use. But if you go and just forget about all of this, start with a huge model, and then start lowering the size of the like decreasing the capacity of the model, you get much better performance, and it's also better performance than with physical constraints. So I think there is a lot of questions here on like can we have models that would perform better without actually any without not understanding the underlying physics? And this is really the eventual question, right? Can I model a system that I don't understand? I think there might be hope there.
On that note, we're going to do one more question, and this is something that Karthik wanted to elaborate on, so I can, if he's still
Sure, yeah.
here.
I can,
yeah.
Yeah, I had a question on super resolution and the ideas that you proposed, Claire, which was very interesting. Instead of struggling to find pairs between high resolution and low resolution, sort of doing the sequence to sequence translation. So I was just curious, I know Mustafa has been thinking about this as well, and likely Pierre as well. So what are your thoughts on good ways to either create pairs for super resolution or sequences for super resolution? Because ultimately, if we were to run a low resolution model and a high resolution model, they diverge because they have different physics, different dynamics. But the goal is that we want to run a low resolution model and somehow use super resolution to create the high resolution counterpart for that, which has the right physics and the right dynamics. So how do we go about doing that?
Okay, so I did not actually talk about sequence-to-sequence translation or super resolution. But the technique that I talked about, the second topic, you just need to be able to get images at both resolutions. They just don't have to be paired, and they could be coming from completely separate processes. Things are going to work better when we can assume that that these are actually IID samples of the respective marginals, right? So do you have any way, maybe NWP or some completely different process of getting the fine-grained resolution maps? That's what the align flow method would need, is samples at both resolutions, just that they don't need to be paired.
I see.
And we also found that they don't even have to be from the same time frame or, you know, generated from the same process. One could be observations, one could be modeled. So it sounds like you have some coming out of models at the coarse resolution.
Yes,
Can you
we do.
use like reanalysis fields or NWP projections or regional climate models for the fine resolution maybe?
Yeah, or I was even thinking of a simpler case of just a single climate model run at 2 different resolutions.
That's, yeah. Actually, somebody in the chats under my talk said something about like somehow downscaling between global and regional climate models. So yeah, that should work as well.
Thank you.
All right, with that, I'd like to thank all of our speakers again today. Wonderful discussion, covered a lot of really good points. So that concludes the lecture portion of our AI for System Science Summer School.